is that exponential equations have a variable in the exponent. They're not going to have a variable anywhere else. If they have more than one variable, it's going to be in the exponent. Every single variable you're going to find in the exponent. And because of that, solving these types of equations become a little bit more complicated. I'm not going to say they're harder. I know that, like you just said, they're complicated. We can't use all of the techniques we've learned already to solve these types of equations. We can't like add 5 and subtract 3 from both sides and divide by 2 and take the square root of both sides, because the x is still going to be in the exponent. So how do we get the x out of the exponent? How do we solve that equation? We need some new techniques in order to do that. The technique we're going to look at today is by taking both sides of the equation and making them have a common base. The base would be whatever's being raised to that exponent. So we're going to look at an example, a couple examples just to practice writing these with a common base. And we want all of these to have a base of 2. So look at your powers chart that I printed out for you guys. Find the powers of 2 on there. And we're going to make all 5 of these have a base of 2. They all look very different at the moment. 32, 4, 16, 1 over 8, 1 over 64 would be the bases. We're going to make all of those bases a 2. So number 1, pretty simple. Look at your chart. Find 32 on there. 32 is 2 to what power? 2 to the 5th. We're done. That's it. 32 is 2 to the 5th power. Look on your chart if you need to. 4 is 2 to what power? 2 to the 2nd power. But notice that there's an x there. So I'm going to change the 4 to 2 to the 2nd power. And that's going to be raised to the x still. The x is still there. All we did was change 4 to 2 squared, but the x is still there. At this point, we have a power raised to a power. And we technically have 2 different exponents. So what is the rule or the property for a power raised to a power? What can we do to simplify that to get just one exponent? You might remember, you probably learned this at some point, maybe? No? We will multiply them. If we have a power to a power, we multiply the exponent. And I write this off to the side. You can write it down if you want. I think it's something you should have learned at some point. If not, you just learned it today. A power to a power, you're going to multiply the exponents. So we're going to multiply the 2 and the x together, and we get 2 raised to the 2x. And now that is a single exponent. Number 3, we're going to do the same way we did number 2. We're going to change the 16, but the 2x is still going to be there. So something raised to the 2x. What is 16? If you need to look at your powers chart, that's 2 to the 4th power. I'm almost certain you're going to get to use a powers chart on your quiz and test. Over this, I will give you a new one. You can write whatever you want to on that one. You won't get to use that one on your quiz, but I'll give you a brand new one. And now we can multiply the exponents again. 4 times 2x is 8x. So we get 2 raised to the 8x power. Number 4, 1 over 8. Is 1 over 8 on your chart? 1 over 8 is not on your powers chart, but is 8 on your powers chart. Yes, there's another property that maybe you should have or shouldn't have learned. I'm not 100% sure about this property, but 1 over 8 we can still write as 2 to some power. And what power would that be? It is going to be a 3, but not just 3. It's actually going to be negative 3. And maybe you did learn that at some point. But anytime we have a fraction, this idea, if you see this fraction like 1 over 8, you do want to use negative exponents. And the property for that is really something like x to the negative n. Let x and n be whatever numbers you want. That's always going to equal 1 over x to the n. And you're like, well, that doesn't really look like that. Well, we can write 1 over 8 1 over 8. 8 is 2 to the third power. And now it does look like this, 1 over 2 to the third. But what's the base there? We still haven't written that as a base of 2. So if we want to write that as a base of 2, the 3 has to become a -3, actually. So anytime you see this idea of a fraction, 1 over a number, you can still look that number up on the chart. Just use a negative exponent in its place, like number 5, 1 over 64. 1 over 64. We're going to look 64 up on the chart, and we're just going to make it a negative exponent. And that's going to take care of the 1 over 64 part. So 2 to the 6th power is 64. So we're going to use the -6th power to incorporate the 1 over 64. We can distribute the -6. We're going to multiply the exponent still. We may have to distribute in this case. -6 times 2x is -12x. And -6 times 1 is -6. So we took 5 things that looked radically different to begin with, and we have changed them, and we have converted them to all have the exact same base. And that's what we're going to do today. In order to solve these equations, we need to make the left and right hand sides have the exact same base, like we just did. It's no harder than we just did to make them have the same base. And if they have the same base, let's use a very simple example, something like 2 to the x. If we had something like 2 to the x equals 2 to the 5th power. Those bases are the same. They're both 2, right? What has to be true about the exponents, the x and the 5? They also have to be the same. So if the bases are the same, so do the exponents. What if the bases are not the same? Can we say that the exponents have to be equal? No. Only if the bases are the same can we say that the exponents have to be equal. So in this case, the bases are the same, so x has to equal 5. And that's really step 2 there. You may have an equation left over from the exponents. Like we might have, instead of just x here, we might have like x plus 1. And then down here, x plus 1 has to equal 5. And then we would solve that equation for x, right? X plus 1 has to equal 5, so x would equal 4. Good. You can always check your work, take your answer, plug it back in, see if the left and right hand sides are equal. But this only works if the bases are the same. So let's do a couple examples. Number 1, 8 to the x equals 4. How do you know what base to use? It does not matter what base you use, as long as you can change the left and right to that exact same base. So here's what I would recommend. I would recommend taking my chart, look at each power, and see if you can find 4 and 8 inside that same power. And that's the base we're going to use. Well, what if you find 4 and 8 in 2 different places? Like maybe it's in the powers of 2, and maybe it's also in the powers of 4. You can use either one. In this case, it's not in the powers of 4, because 4 to a power is not 8, at least a whole number. So we're going to use powers of 2. So I know that my base in this case must be 2. Is it sometimes possible that the base could be one number and then somebody else use a different number? Yeah, that is possible. But in this case, we're going to change 8. 8 is 2 to the 3rd power, and that's being raised to the x. And then 4 is 2 to the 2nd power. So we're going to do literally what we just did on the left and right hand sides of the equal sign. We're going to multiply any exponents that are being raised to exponents. So like the 3 and the x. So we get 2 to the 3x equals 2 squared. And now what do we know about the bases? The bases are the same. And if the bases are the same, what has to be true about the exponents? They have to be the same as well. I'm going to do this one time. I'm going to show you that this is mathematically incorrect. And some of you might be inclined to try to do this. And you might come in here and you might like cancel those 2's out. Cancel those bases out. Mathematically, nothing that we've done actually canceled those bases out. They don't cancel out. There's nothing we can do to cancel them out. But what we are using, so don't do that. But what we are saying is like, hey, the bases are the same. The bases are the same. They don't cancel out. But I know if the bases are the same, the 3x and the 2 must be equal. So just don't cross the bases out, please. Mathematically, it's incorrect. I know you might want to, like, oh, the 2's go away. Not really. The 2's are actually still there. And then we can divide by 3 on both sides. That's what I did here. Divide by 3 on both sides. The 3's cancel out. And we are done. It's perfectly okay that you get fractions. Most of your classworks, you're going to get a fraction as the answer anyway. All right, number 2. I would look at my powers chart. I would try to find 27 and 81 under the same power. It does not matter what power you use. So if you find 27 and 81 in like 2 different places, which one do you use? It doesn't matter. As long as 27 and 81 are both one of those powers. In this case, I think you can only find it under the powers of 3. So we're going to change 27 using our powers chart if you need it. 27 is 3 to the 3rd power. That's being raised to the x. 81 is 3 to the 4th power. So 1 over 81 is going to be 3 to the negative 4th power. Fraction, use negative exponents. Why negative exponents? Some mathematician started doing that, and then everybody said, oh, I like that idea. Let's do that. So now it's just like common knowledge that that's what negative exponents mean. So 3 times x is 3x. So 3 to the 3x equals 3 to the negative 4. The bases are the same. Exponents must be the same. So 3x must equal negative 4. And we can divide by 3 on both sides to get x by itself. Fractions are perfectly okay. Nothing wrong with a fraction.
We use mixed numbers.
If you would like, the answers I give you in the multiple choice problems on the test are probably not going to be mixed numbers. But mixed numbers are okay. Yes, you need to know that x equals negative 4 over 3. Because we are solving for x. We're trying to figure out what values of x would make the left and right side of the equation true. So yes, we do need the x equals negative 4 over 3. That would be our final answer. Try number 3. I'll give you a minute or so. It looks a lot like the one we just did. You're going to look for 125 and 5 under the same powers chart. And you should have found that under the powers of 5. And since the right side is already a 5, don't change the right side. Only change the left side for number 3. Do not change the right side. It's already 5. That's what you want it to be. So only change the left side of number 3.
Didn't we say it's equal for number 1? Yeah.
I'll scroll up so you can see it. I'll give you a few more seconds to work on number 3 before we go over it together.
Okay. Number 1, why did we put everything over 3?
At first it looked like this. It looked like this at first. So to get rid of to get x by itself, we had to divide by the 3 on both sides. So it looked like we put everything over 3 because you couldn't see me work it out just by looking at it. But to get rid of the 3 attached to the x, we had to divide by it. Alrighty. Number 3. We got 1/125. You would have found that on your chart. That's 125 is 5 to the third power. So 1/125 is gonna be 5 to the negative third power. And that's gonna equal 5 to the 3x. If you don't always have to change both sides of the equal sign. We're just trying to get them equal. So if we only need to change one side, that's good. That's good. So now that the bases are the same, we can say that the exponents, -3 and 3x, also have to be equal. We're going to get x by itself. So we're going to divide both sides by 3. Yet again. Third time today. 12th time for me today. -3 divided by 3 is -1. -3 divided by 3 is -1. Number 4, I wouldn't say number 4 is harder. It does just bring in the exponent, looks a little bit complicated. We got the 1 minus 2x there. So maybe when we start solving that equation, maybe there's an extra step thrown in. If you look at your powers chart, you want to find 3 and 243, and you'll be able to find them in the powers of 3. And 243 is 3 to the 5th power. So we're going to change 243 to 3 to the 5th power. Now that those bases are equal, what can we say about the exponents? We know that 1 minus 2x has to equal 5. You should hopefully be able to solve that equation at this point without my help. You've been doing that since like 7th, 8th grade. So you should be able to subtract 1 from both sides and divide by -2. Hopefully, at this point. If you can't subtract 1 from both sides, or if you're not sure, like, man, I see you doing that, I just really have no clue about that. You really probably need to come get some help, because you're gonna be struggling in math for a long time. If you can't solve a two-step, what we would call a two-step equation. And then the -2, we're gonna divide by -2. Well, it's negative, why didn't you add? Because we're multiplying, times the x. So that's a common mistake. People add the 2 because it's negative. But we gotta divide by it because it is being multiplied by the x. You see the minus sign there, and like, you wanna add it, but it's being multiplied by x. So subtract it, not subtract it, divide it. 4 divided by -2. So our final answer would simplify to -2. Number 5, we will have to change both sides in this case, because you will not find 9 and 27 under the same power chart. You will not find 9 and 27. Yeah, that's what I meant. You will not find 20s. I don't know what I was trying to say. You will find them under the same powers chart, but not under the 9 power. Because like 9 to what power is 27? It's not going to be on your powers chart. It's not going to be a whole number. There actually is a way, but it's not a whole number. So if we're going to use whole numbers as exponents, we have to change both sides in this case, and it would be 3. You are correct. What I said was very wrong, and I'm not editing the video for YouTube, so it'll be okay. 9 is 3 squared. And that's still being raised to the 2x minus 5. Yeah, what I meant to say is we can't use powers of 9, because the left side was 9, because 9 to a power is not 27, not a whole number anyway. And then on the right side, 27 is 3 to the third power. This brings in the idea that, hey, I need to distribute the exponent on the left before we set those equal to each other. So we're going to have to multiply by the 2 on both sides. Or 2 times 2x, which is 4x. 2 times -5, which is -10. And that's equal to 3 to the third power. 3 to the third power. And now that the exponents have been distributed, the bases are equal. What do we know about 4x minus 10 and 3? We know that those have to be equivalent. The bases are equivalent. The exponents have to be equivalent. You should be able to solve this equation. Add 10 to both sides. 4x equals 13. And divide by 4 on both sides. You can just leave it 13 over 4. That's fine with me. And we'll save the discussion about decimals for later. I would prefer the fraction for now. Number 6. If you can do number 6, you would be able to do any problem like this that I give you on a quiz or test. It doesn't really get much harder than number 6. It doesn't really get much harder than number 6. So if you want to try number 6, I'll give you about 2 minutes or so before I start working it out. If you've already done it, that's good. If you haven't done it, you can try it. If you don't want to try it, just hang tight. We'll go over it together in just a second. If you do go back and watch these videos, you can always pause them, rewind them, fast forward them, watch what you need to watch. Skip parts if you don't need them. Because I'm not editing them. I don't have time. Unless they make an announcement and say somebody's name or something. I'll go cut that part out, but that's it. You're gonna find 27 and 9 on the powers chart under the same power. And that would be under the 3, the powers of 3. Got to do lots of distributing here. I got to use some negative exponents here. Got to change the 27 and the 1 over 9. So if you're stuck, look at your powers chart. 27 is 3 to what power? 27 is 3 to the third power. We need to change 1 over 9 to have a base of 3. 9 is 3 to the second power. So negative 2, 3 to the negative second power, would make it 1 over 9. We're going to do some distributing. We're going to distribute on both sides. And then we can solve an equation. 3 times 2x is 6x. 3 times 3 is 9. Negative 2 times 2 is negative 4. And negative 2 times negative 2 is positive 4. The bases are equal. Do what? Not yet.
No, but it's 2x negative, or 2x minus 2, but we take it to 4.
Yeah, we're multiplying those together, so it'd be negative 2. It'd be negative 2 times negative 2, not negative 2 minus 2. We are multiplying. So then we get our exponents. 6x plus 9 and negative 4x plus 4 would be equivalent. At this point, we have x's on both sides of the equal sign. I don't care what the rest of the equation looks like, but if you have x's on both sides, we want to move all of them to one side, probably the left typically, because that's what most of you are going to do. And if it doesn't have an x on it, we want to move it to the right side. So the 6x has an x. I'm going to leave it on the left. The 9 does not have an x. So I'm going to move it over here to the right side. And then I'm going to go ahead and look at the right side. The negative 4x has an x in it. So I'm going to move it to the right side at the same time. We can do it all at the same time, no worries. And the 4 doesn't have an X in it, I want it on the right side. So 6x plus 4x is 10x. And 4 minus 9 is -5. We're gonna divide both sides by 10. And then we're gonna simplify the fractions if they can be simplified. Your calculator will simplify most of them. But in this case, 5 divided by 5 is 1, and 10 divided by 5 is 2.